Chemical equations are shorthand representations for chemical reactions. As we see, the reactants are shown on the left, the products are shown on the right, and the chemical equation is represented by this arrow. The chemical equation expresses the identity and quantity of the substances involved. Let's look at a specific example. Sulfur trioxide dissolved in water produces sulfuric acid. This is our balanced chemical equation. We can look at this and interpret it on a particulate view, which is a molecule reacts with a molecule to give a different molecule. We can also interpret a chemical equation on the everyday level, or the macroscopic view, in which a mole of our reagents react, in this case to give us a mole of products. Or on the mass balance view, if we had 80.06 grams of sulfur trioxide, which is the mass of 1 mole, reacting with the mass of a mole of water, we get the mass of a mole of sulfuric acid. The major aspects of concern to chemists are the mass relationships between reactants and products, or the stoichiometry, the classification of reaction type, for example, precipitation, redox, acid-base, and the heat that's involved in these chemical equations. Balanced chemical equations are always written in a way in which mass is conserved. This is illustrated by this cartoon. This here represents a molecule of SO3. This is a molecule of H2O, and we see represented here the constituent atoms of each molecule, and this represents our product H2SO4 and its constituent atoms. The scale here is represented as being balanced, i.e. the mass of the reactants is equal to the mass of the products. As chemists, we know the equation is balanced when we have the same number and type of each atom in the reactants as we have in the products. Sulfur is represented by this yellow sphere, and we see the element sulfur is balanced. We have 1 atom of sulfur in the SO3 and one atom of sulfur in H2SO4. So we can see both from the representation of the atoms and molecules as well as the chemical equation that we have 1 atom of sulfur on each side. If we look at hydrogen, there's 0 hydrogens in SO3, but we get 2 hydrogen atoms contained in water. And if we look at sulfuric acid, we have our 2 hydrogen atoms. So there's a balance of hydrogen atoms. And finally, the oxygen. This SO3 molecule has 3 atoms of oxygen, and H2O has 1 atom of oxygen. So we have a total of 4 atoms on the reactant side. On the product side, we have also 4 atoms of oxygen. Additional practice interpreting chemical equations illustrate mass balance on these following chemical reactions. Methane, 1 atom of carbon in the reactants, 1 atom of carbon that exists in the products. For the hydrogen, we have 4 atoms of hydrogen from methane, 3 atoms of hydrogen from the ammonia, for a total of 7 on the reactant side. On the product side, we have 1 hydrogen atom in HCN, and we have a total of 6 hydrogen atoms from the 3 H2s. So there's 7 hydrogen atoms on each side. For nitrogen, we only have 1 nitrogen atom. It exists in the ammonia molecule, and 1 atom of nitrogen in our products. We see the representation of the combustion of methane. Combustion of hydrocarbon and oxygen is going to give us carbon dioxide and water. And further, we see that this chemical equation is balanced. Let's look at carbon. Carbon has 1 atom in the reactants and 1 atom in the products. Hydrogen, 4 atoms here in the reactants and 2 times 2, 4 atoms of hydrogen in the products. Oxygen has 4 atoms of oxygen in our reactants, and 1, 2, 3, 4 in the products. 2 in CO2 and 1 each from each of the 2 waters. So thus we see our balanced chemical equation is balanced. That we have the same number and type of atoms on the reactants as we have in the products. A final example of the particulate view of a balanced chemical equation is the combustion of octane, the primary component of gasoline. We have 2 molecules of octane that are going to be combined with 25 molecules of oxygen to yield 16 molecules of CO2 and 18 molecules of water. And if we did the simple math associated with each element, we would see we have the same number and type of each atom in the reactants as we have in the products. There's additional information that we can find in balanced chemical equations. Often the phases are indicated. The AQ means that this substance is aqueous or dissolved in water. S refers to a solid, L for a liquid, G for a gas. Special conditions of the reaction is sometimes indicated by notations above or below the arrow. For example, if you see the uppercase Greek delta associated with an arrow, that represents heating that occurs. Here, this equation could be interpreted that the roasting of calcium carbonate or limestone, if we heat calcium carbonate, the products of calcium oxide and CO2 are going to be produced. In your notes are a number of chemical equations you can practice balancing. These blanks before the formula indicates you are to fill in this blank with the appropriate coefficient. The coefficient tells us how many we have of each of these molecules in order to have a balanced chemical equation. The best way to learn how to balance chemical equations is to practice balancing chemical equations. There are some hints that tend to make things easier. In general, you want to start with the most complicated looking chemical. Balance each of the elements within this chemical and then go on. In general, keep your polyatomic ions together and count them as a unit. And you can only change the coefficients in front of this formula, because if you change the subscripts, that's changing what that chemical is. It's changing the identity of the chemical, a no-no. So you only change the coefficients in front of these chemical formulas. So let's start with our glucose here. If we have 1 molecule of glucose, that means we have 6 carbon atoms. So we're going to need 6 CO2 molecules because the only place carbon exists in the reactants is in CO2. 12 hydrogens means that we're going to need 6 water molecules. So 12 hydrogens, 12 hydrogens. Okay, now as far as the oxygens, let's look at how many oxygens we have in the reactants. We have 6 times 2, 12, plus 6, so we have 18 oxygens, and we have 6 oxygens here in the glucose, so we need 6 oxygen molecules to balance out oxygen atoms. A quick sanity check. We have 6 carbon atoms in the reactants, and we have 6 carbon atoms in the products. For hydrogen, we have 12 in the reactants, and we have 12 in the products. Oxygen, 12 from CO2, and 6 from the water. So we have a total of 18 oxygen atoms in the reactants and the products. We also have 18 oxygen atoms, so we're balanced. For this next problem, we have a little bit of practice with nomenclature, as well as practicing analyzing a question. You see aqueous solutions of calcium chloride and silver nitrate are mixed. So these two chemicals are reactants, and we're told a precipitate of silver chloride is formed, so this is the identity of our products. Calcium chloride. Calcium is a 2A metal. We know it's going to have a 2+ charge. Chlorine, 7A, it's going to have a -1 charge. So to write the formula of calcium chloride, we combine these ions in a proportion so that we have a net neutral compound. That means we're going to need twice as many chlorines as we have calcium ions. We know here that we can use our shortcut of exchanging these numbers to produce a neutral compound. And silver nitrate. We know the charge of the nitrate ion is -1. Therefore, the charge on silver is +1. Plus, we know silver is always going to have a +1 charge. So this is our formula of silver nitrate. By similar considerations, we can get the formula of silver chloride, and we can predict what the remaining product is. Because we have unaccounted for in the products the calcium ion and the nitrate ion. So our remaining product we know is going to be formed from calcium 2+ and nitrate. And we'll need twice as many nitrates as we have calcium 2+ ions. So that formula is CaNO3 quantity 2. So we can write our first draft of the chemical equation. So we have calcium chloride is going to react with silver nitrate to give us silver chloride and calcium nitrate. Now we can balance our chemical equation. Let's start with our calcium nitrate. If we have one of those, then we're going to need 2 silver nitrates because we will need 2 nitrate ions. This is what we meant by keep polyatomic ions together. Now this is a general strategy. Sometimes the polyatomic ions react, but more often than that, the polyatomic ions stay together. So continuing on, if we have one of these calcium chlorides, we're going to need 2 silver chlorides, and that also balances the silver, so we're done.